I'm Ira Flatow. Hope you are Science Friday listeners. I am not David Paymer, who I have to sign autographs for a lot. I want to welcome all of you to our deep dive, which is entitled Why We Explore, Deep Dive Space. And I'm very excited about this deep dive because there's so much going on in the world. And this like we have two worlds, the world of politics and the world of discovery. And we've been talking a lot about politics and talking about the world of discovery and what has been going on in space recently. It's just mind-boggling. So in our deep dive today, we're going to talk about two different areas of space. First deep dive, we're going to talk about what's up there in space. I mean, some of the greatest discoveries now about planets, exoplanets, newest stuff from Pluto. I did say the planet Pluto, if you were paying attention. I thought I was going to separate politics from science, but that doesn't work. And then we're going to also talk about all kinds of crazy things like black holes, dark energy, dark matter, all kinds of really weird and wonderful discoveries and explorations in there. And to start us off on a sort of an overview, I want to introduce David Aguilar. He is the past director of the Science Information and Public Outreach at Harvard Smithsonian Center for Astrophysics in Cambridge. He has been a popularizer of science. He's been a science expert. He's been involved in all kinds of science in the public. He's a naturalist, an astronomer, an author, a space artist. He can communicate science to everybody. So if you've watched the PBS Nova series, if you've seen him all over the place, you'll recognize him immediately when he comes up here to talk about. So I'm going to let David give us a little brief overview of the deep dive. David, come on up.
I must say, what a wonderful pleasure to be here. And I will admit right up front, I am a space junkie. I love outer space. And when we were talking today about why we explore space, I realized that I have had my feet in many different worlds, from aerospace to scientific research to working with kids in Science Museum, writing children's books for National Geographic. And when I saw this title, I realized that this was absolutely an adult question, because children never ask this question. And I thought, well, we now deal in different worlds. We all once were children, and life might have been a little bit simpler for us. But in this world today, we are bombarded with terrorism, with guns, with politics, with the threat of climate change, so many things around us that grab our attention. We think about finances, we think about money, we think about what governments can do, where we can go with that money, how is it best spent? Do we really need to spend it on outer space? And so with questions like this, and with a life that is constantly being distracted with the Twitter sphere, Facebook, Snapchat, LinkedIn, all of the crises that continually confront us, things that we need to deal with, the horrors of restless leg syndrome, all of these things that we deal with, where children don't. And so when I looked at this topic, at first it seemed very logical to me. And then I realized it was a little bit more. So these are my thoughts, and these are my ideas as to why we explore space. First of all, it's big business. Last year, we spent a total amount, the world, of about $25 billion to research space. NASA, ESA, the Russians, European Space Agency, the Russians, the Chinese, the Japanese, the Indians, Canada. This is what we spend every year to explore space. This is not chump change. This is a lot of people being employed. So consequently, right up front, space is a business, and this is what keeps some of our economies rolling. Secondly, space is rapidly changing. It is now becoming commercialized. And as space becomes commercialized, a whole new arena of entrepreneurship, new jobs, programmers, engineers, marketers, lawyers, because we're even going to have to come back and take a look at treaties as to how they apply to outer space. So it's a burgeoning market that has just taken off. When we take a look at some of the people who are now involved, billionaires who've made their fortunes in other fields who are rapidly investing in outer space, this is where the economy and the economics of tomorrow is coming from. Jeff Bezos, Elon Musk. We can go down and down the line of all the new space corporations that are being formed to develop space. Space tourism. How many of you have seen the little commercials for riding that slide in LA? You're 1,000 feet up. You come down on that glass slide, one story, and people are loving it. Just wait in a few years till you take your family into low Earth orbit, 60 miles above the Earth, and you look out the window. That's going to be an experience. So consequently, this is also money. This is also business. And in fact, the little country of Luxembourg is now looking at leading the world in space mining. Right now, there are over 13,000 what we call near-Earth objects. These are asteroids that either cross the Earth's path or are very close to our planet. We want to mine them. They have platinum, they have gold, they have tremendous amounts of very rare elements we find here on Earth. And the little country of Luxembourg, which is known in Europe as the investment center of Europe, is now fully investing in space mining. So now we'll have miners that live on asteroids as they travel through space. That's what's coming. So you see, why we explore space? It's business. It's big business, and it's just going to grow. But that's not the only reason why we explore space. And this is the one that when I delved deeper into it, really struck home. There is something different about our species. There is something different about us that we apparently do not share with any other creature on this planet. And Stephen Hawking at the Pluto mission meeting we had last August said it best. He said, "We explore because we are human. We want to know." And that defines something in us. When we think about exploring, you've got to think back to our own history. It's an intriguing history. 2 million years ago, ancestors that would soon become human beings in the annals of time decided it was a great idea to put the cave up for sale, put the kids on their back, and move, and start spreading out over the world. Now, the interesting aspect of this is they didn't have to do it. They weren't resource challenged. There was really no reason for them to get up and start dispersing and moving, except they had to do it. This is what intrigued me when I took a look at humans and why we reach out as we do. 17,000 years ago, somebody decided it was a grand idea to come across the frozen Bering Straits into a brand new world. We called them the Clovis First people. And as they got to this new world, the Americas, they must have just been astounded as they stood back, looked at all of this, and they thought, oh my God, think of it. All the shopping malls, all the condos, all of the different shopping areas we can put here. It's wide open to us for development. And now we had migrated to another part of our planet where humans had never set foot before. But it continued. It continued. When Captain Cook did his own Brexit from the British Union, he left 3 times to sail to the South Pacific. When Roald Amundsen decided that he needed to go to the South Pole, crossing the Ross Ice Shelf, This was something in us that drove him to do it. And even Jacques Cousteau in 1945 decided it was time to build something that you could carry with you and humans could explore the underwater world. No more were they trapped on the surface looking down at a distant landscape. We suddenly became part of it. And I started asking myself, what is different about humans? Why do we explore? What is it that drives us? I think Herman Melville said it best. In Moby Dick, some of you may remember this famous line, he really defines who we are. He said, I am tormented with an everlasting itch for things remote. I love to sail forbidden seas. Itch is the word we need to focus on here. So is there something itchy inside of us as a species that makes us explore, to travel to areas that sometimes we have no business being in, and yet there we are? And the answer may be as basic as our own genetic makeup. If you look deep inside of us, we have genes. What are genes? Genes are little DNA-encoded capsules that we all carry inside of us. And they dictate our heredity. They dictate who we are. You have blonde hair, you've got 2 genes for blonde hair. You have brown hair, you have a dominant gene in your body. You have green eyes, you have blue eyes, you have gray eyes. You're left-handed, you're right-handed. All of these are determined by our genes. Even our susceptibility to being ill and to different afflictions of the human body, even mentally, appear now to be connected to our genes, these programs that we carry in our body. And I think one of the most fascinating of all the genes we carry is this one, DRD4-7R. The first part is its location. 7R dictates what this gene is. Why? Why is this an interesting gene? Because people who contain this gene are different than other people. They love to explore. They love to travel. They love new adventures. They are willing to try new foods, new sexual relationships. They're willing to try drugs. They are willing to change their lives because they have a thirst for new knowledge. These are the people who carry this gene. They are our explorers, and they are most certainly open to change, which makes you think that the majority of our Congress today does not carry this gene. So how much of us carry it? 20% of the world has this gene inside of it. And I'm laying money down right now, I'll bet almost everybody in this room is carrying that gene in their bodies, or you wouldn't be here. The new knowledge, the new experiences, the new people you're going to meet, the new ideas you're going to embrace, and possibly change old ideas. This is the restless gene that's part of us. Maybe this is why we explore outer space. Makes sense. So it's business and it's money, it's employment. It's that restless gene we carry around inside of us. But then again, the exploration of space is something else. Face it. Outer space is not a friendly place for human beings. We don't do well in outer space. We start losing our muscular structure. Aboard the space station, they're constantly taking a look at this and how do we change this for long-duration flights to Mars and beyond. The human body does not respond well to zero gravity. We even start losing our eyesight capability. We start getting tunnel vision as we spend more time up in space. We all know if you step outside this spacecraft without a spacesuit, your blood is going to boil away. Space is not a place that is kind to human beings. And face it, for the layperson in this country, outer space doesn't necessarily make them happier, wealthier, doesn't make them prettier or handsomer. It really doesn't change their lives in any appreciable way. And yet we have this odd fascination with astronomy. And the fascination is simply put to you this way. How many of you right now, raise your hand, can name 3 famous botanists? Go for it. Okay. I'll make it easier. Name 3 famous chemists. Go. 3 famous geologists. 3 famous meteorologists. Name 3 famous astronomers. Here we go. Einstein, Hubble, Sagan. It goes on and on. There's something about astronomy that touches our soul. I think when we think about astronomy, Isaac Asimov said it best. He said, whatever else astronomy may be, who can doubt it's the most beautiful of all the scientists? And this is how children see the universe. And that's why I said in the beginning, it was an adult question. Because for many of us, we've lost that contact. But we get it back when we see these remarkable images from space that tell us it's a wonderful place to conduct business. It's a wonderful place to explore because we just can't help it. But lastly, it is simply stunningly beautiful. It's the wonderment of space that spurs us on. Thank you.
While we're waiting for our panelists to come on up, I'll just welcome you all and follow on David's incredible words over there, because the kind of space we're going to talk about first is not any place you can physically go to. It's a kind of space that it's the universe. It's way out there in the universe, and we're going to talk about what is the universe made out of, and why don't we know what 96% of the universe is made of? And when you think about it, we'll talk about it. When you look around, you see the lights, your family, everything else, everything visible in the universe is only 4% of the universe. And the rest of it is 96% is made out of dark energy, dark matter, dark stuff that we really don't have any idea what it is. And black holes, stuff like that. And that's what we're going to talk about, exploring that stuff now and how we're able to explore what it is and how fascinating it is. So I'm going to start a panel discussion over here. Let me start over. Lisa, why don't you introduce yourselves? Everybody introduces people. I'm going to have everybody introduce themselves and say what they like.
Each other.
Yes. Lisa, why don't you go first?
Thank you. I'm Lisa Randall. I'm a professor of physics at Harvard. I've also written several books. The latest one is called Dark Matter and the Dinosaurs. The others are more particle physics. I'm probably a little bit of an outlier here because I study what I guess some people will call inner space, but I'm really a particle physicist, so I study the structure of matter. But that leads me to, believe it or not, questions about outer space as well, because we want to know what's out there. We want to know what the fundamental stuff is that everything is made of. So in terms of exploring, we're not just exploring the outer universe, we're exploring inside as well to try to figure out what all this stuff is. And I guess that's
great.
An introduction. Okay.
Janna?
I'm Janna Levin. I'm a professor also of physics, but also of astronomy. And I don't know, who am I? These days I'm having an identity crisis. I'm also director of sciences at a place called Pioneer Works in Brooklyn, which is mostly an art center, so that's a little bit off the mainstream. And like my friends here on the panel, I'm an author of books. I'm signing books at 410, come see me, so I'm not sitting there alone. We spoke about it this morning. The book is called Black Hole Blues and Other Songs from Outer Space.
Great. Lawrence?
I'm Lawrence Krauss. I'm a professor of physics and astronomy, but also now the School of Earth and Space Exploration at Arizona State University. And I direct something called the Origins Project there, which looks at everything from the origins of the universe to the origins of consciousness and social institutions. my background actually is particle physics, as is Lisa's.
You know, I took my qualifying exams in particle physics.
That's right. And I was going to say I've been a professor of physics and astronomy as long as you've been alive, but no. Anyway, and I write books and do other things, but I refuse to mention the name of any of my books.
Okay, I won't mention my last book. Let me just go this way then, Lawrence. What is out there in the universe, the dark stuff? Why is that so mysterious, and why do we know so little about it?
Well, we know so little about it because it's dark, and for the longest time we used telescopes. But it's important because it addresses those fundamental questions that we all have. Why are we here? How did we get here? The reason that we exist, this planet exists, is due to certainly to dark matter, because we've known for a long time that galaxies couldn't have formed if this dark stuff hadn't collapsed first. And dark energy is the dominant stuff in the universe that will determine, we think, the ultimate future of the universe. And so it's important because ultimately, if we took everything we can see today, everything we could see with optical telescopes, all the beautiful images that you're shown here, it's all irrelevant. It's a 1% bit of pollution in a sea of dark matter and dark energy, and that determines what will ultimately happen to the universe. So to me, what's most important about it is it puts us in perspective as a bit of pollution and a little bit of a sideshow in the universe, and it makes us, in some sense, realize how lucky we are in this sideshow to have come about, as I'm sure Lisa will emphasize too. These exotic things ultimately are responsible for this remarkable experience in Aspen we're now having.
Lisa, can you want to amplify what he said about these little particles and these things and why they're important?
You know, it's funny. It's a real question of what we mean by important. I mean, we all exist here every day, and we're in a place where ordinary matter is really dense. We live in the Milky Way disk. I love being in Aspen because it's one of the places where you can actually see the Milky Way disk. Yeah. So, you know, we're surrounded by this halo of dark matter. It's mostly diffuse, but the Milky Way disk is dense matter. Yet our whole galaxy, the reason the matter was able to organize and form stars, and form galaxies, form stars, was because dark matter was there to bring everything in. Without dark matter, at least in the lifetime of our universe, it could have gone on without, but in our universe, in the lifetime of our universe, dark matter, there's 5 times as much of it as ordinary matter. So stuff could actually begin to form structure first, because if it was just light, as you know, light doesn't organize, matter does. And also, oddly enough, the fact that it doesn't interact with light helps, because light would wash out the structure. It would sort of be like wind on a, if there was a structure of sand and a beach, the wind would wash it away, and light would do the same thing. But dark matter doesn't interact with light, at least our light, the light we're familiar with. It's not actually dark, it's transparent. We do see dark things like Janna's pants, but it's transparent, so light just passes through. Billions of dark matter particles are passing through now. But the fact is, it doesn't interact, which means enormous amounts of it can have effects.
So is it like gravity, dark matter? Is it attractive?
Well, it interacts via gravity. And one of the big questions is, does it interact only via gravity? The only way we've seen it so far is through its gravitational interactions. But the real question is going to be, does it have other interactions?
And in that regard, it's kind of fascinating, because most people don't realize that gravity is the weakest force in nature, by far weaker than any other force, orders of magnitude weaker. The only reason when you get up in the morning that it seems important is that every atom in the earth is attracting every atom in your body. And so if it just interacts by gravity, everything interacts by gravity, and that's how we've been able to infer its existence. But it could have very, very weak interactions, far weaker than anything that would allow it to be visible, and still overwhelm in some ways its gravitational interactions, which is why it's an interesting question. But it is, as Lisa said, that very important fact that normal matter just couldn't collapse because it interacted too much and released light. So
yeah, in fact, it's so weak, your kitchen magnet can overcome the force of gravity. A little magnet like that.
Richard Feynman gave a great experiment. You should all try it, so there's no tall buildings in Aspen. Just take a friend to the top of a tall building and push them off. And then it takes maybe 100, 200 feet for the entire Earth, the gravity of the entire Earth to accelerate them down, but electromagnetism does it in a fraction of an inch. They don't even make a dent in the concrete.
Let's talk about another great mystery in the universe, and that are black holes, Janna.
Yeah.
Give us a little thumbnail sketch of what a black hole is and why
Can I just say one thing before? Dark matter and black holes are different. A lot of people actually confuse them.
Although,
And dark
yeah.
matter, dark energy, and black holes are different. They all have dark or black in them, but they're all different things.
There are some people who are promoting this kind of strange
Oh, absolutely. That's
suggestion that the
possible.
dark matter could be black holes,
Right.
but they don't need to be black holes.
It was one of the first candidates that people thought of as in
Yeah.
the long list, and sort of most black holes have been removed as candidates, but there's still some small ranges.
Yeah,
where
I mean, the only reason why they're coming up in the conversation about dark matter is that they are, in fact, technically dark. They don't emit light or reflect light. And like dark matter, the only effect you can really glean from them is indirectly through the gravitational effect that they have on the space and time around them. But people, I think, often think that a black hole is a collapse or a dense crush of matter. And that's actually not what a black hole is. In fact, a black hole is nothing. A black hole is an empty region of space-time. The only way that we are sure black holes form has to do with taking matter and crushing it densely, like the collapse of a very heavy star. But once the star collapses and space-time becomes so strongly curved around it that not even light can escape, it like inscribes a shadow on space-time behind it, this material, and then it keeps falling. So the shadow, what we think of as the black hole, this region beyond which not even light can escape, is actually empty. And the material
what happens to all the
formed
stuff that
it-
goes into
well,
it?
that we don't know. We know it has to continue to fall, and then there's a lot of arguments that maybe it leaves behind a remarkably small quantum remnant, but that's very unpopular for many reasons. Maybe it blows out into a different Big Bang, also unpopular for many reasons.
It's also worth mentioning that black holes they're still inferred. We still aren't certain that black holes exist. There are things that walk like a duck and quack like a duck, and we think they're ducks, but we see things that so far we can only explain as if they're black holes, but we don't have any in the lab that we can.
Well,
So I think the more fair way of saying it is that we don't really know what black holes
Yeah,
are.
yeah.
I mean, I wouldn't exactly say they're empty. We know that somehow, if quantum mechanics is right, that the information that went in should somehow be there. But we don't know what it is. I mean, the space-time metric changes as you go inside. The form of matter changes as you go inside. So there's a lot of open questions. So whatever it is that's there, we're going to call a black hole.
But it's even more open than
We don't
that.
even
I
know.
mean,
Well, I
we
think
don't
it's-
even know that black holes exist. Some people like me have written papers saying maybe they don't even form.
Well, look, I think if we say something like we look at stars orbiting the center of our galaxy, and we
Yeah.
see that they're orbiting an empty region of space that's millions of times the mass of the sun, but fits in about 3
Yeah.
sun widths. And most people are pretty happy to call that a black hole. Now, technically, what I consider to be a black hole really is the existence of the event horizon.
Yeah.
And that is empty. That's inarguably, I think, empty. I mean, unless we're going to talk
event horizon is the edge of the
Right.
black hole.
The center might not be empty, but the event horizon better be if we know anything about what we're talking
Although
about.
people now, I mean, there is a lot of debate about that.
Right,
because
but
there's a lot
at
of
the
debate
quantum
about
level.
what's at the surface of the black
Yeah.
hole.
All of you think
We're
that
gonna-
scientists
we're gonna-
agree about everything. I want this to be.
But it's really
I want this to be a lesson.
No, but the point is let's say we understand something better about quantum gravity. We decide that there's a smear of strings that are in some kind of holographic way smeared out around the horizon, and it's not truly empty, et cetera. It won't change the fact that there's this object that's millions of times the mass of the sun and fits.
We'll agree there's an object there.
But it's
But the objects, but then we had this, if they didn't exist, how did we get this new gravitational wave? The black holes were circling
they're
each
dense
other.
objects, and they act like black holes, and they could easily be black holes.
Whatever it is, it's walking like a black. It's quacking. What's the
Exactly.
expression? It's quacking like a black hole. It's walking like a black hole.
It's worth pointing out that this is the limit of science, and it's really, we're all theorists. And we need observations and science is it's empirical. And where we're at the limit of our empirical knowledge is where you see people like us arguing the most. And that's really important, that we can't come up, it's not just theory, we
But I
need
want to say
observations.
something else that's important, which is that a lot of fundamental science these days is stuff we sort of infer indirectly. I mean, the existence of dark matter, I mean, but in some sense, at a very deep level, everything is inferred indirectly. I mean, we can say we see things with our eyes, but everyone knows our eyes are unreliable. A lot of processing goes on. So basically, when we observe anything, it's an interpretation in terms of fundamental theory. And it's not even necessarily a fundamental theory, it's an effective theory. And the fundamental theory can change what's really going on inside. I mean, when we say we see a podium here or a table, what do we call this thing? I don't know. We see it, but we know deep down it's made up of atoms and molecules, and most of that's empty space. Do I say that's empty space? No, I'm still going to call it a table. So from the point of view of an effective theory, we have seen black holes. From the point of view of effective theory, we have seen dark matter. And that's a really important, especially for someone who cares about science and religion so much, it's really an important distinction to make, that we infer things, a lot of things indirectly.
I think another important takeaway is the reason why we're splitting hairs on these issues of whether it's truly empty space or not empty space is because it's important to us scientifically now. These are really important questions, and the black hole is the terrain on which we're working out some of the most difficult and subtle aspects of absolutely forefront theory. So we're all open. I mean, if tomorrow somebody proved to me that that thing at the center of our galaxy was not actually what we conventionally mean by a black hole, I'd be thrilled. I wouldn't be disappointed. I'd be thrilled because we'd be making progress on the most difficult front. No, I think that could still, you know, it's like...
And to get to your question, that's the connection. Black holes, dark matter, dark energy, they all connect the largest things we can see with the fundamental stuff that makes the universe up. There's this beautiful connection. And so they are wonderful laboratories, which is why, I mean, I was trained as a particle physicist, why 30 years ago I started getting involved, because we're limited with terrestrial, I mean, we have the Large Hadron Collider, which is a wonderful machine and an important machine, but to explore, the universe was a huge particle physics experiment that was done at least once, and it's data analysis now, and it provides us an opportunity to a new observational handle to learn about the kind of questions that we care about.
Let's talk about the gravitational waves then, because this was the second one was detected just a few weeks ago, a couple weeks ago.
It was announced.
It was announced.
Announced.
They
It was
did.
detected.
You were there when they detected the first one, were you not?
I wasn't well, I was sort of there. So I was working very closely with the team, and two of the original architects, Kip Thorne and Ray Weiss. On the day of detection, I happened to print a draft of the book for them to peruse, and they didn't tell me about the detection. I am not signed an MOU to be, I'm not an experimentalist, but they did tell me very early on, and they were accusing me of leaking it to you, Lawrence, which
I'm happy to say you were not my source.
This was last fall,
Not my
right?
source.
Thank you for publicly
I leaked
saying
it to
was
the
not
public
your
as I
source.
think it's appropriate.
But yes, they did tell me very early about the detection.
They told you not to write your last chapter, right?
They gave, yeah,
said
they
there
wanted
was
me to
something
write-
that you're going to be missing if you
Yeah.
don't hang around.
Yeah, they didn't want me to go to press without the discovery as the last chapter.
So what are, I mean, if we look at space, what are gravitational waves? What is happening, Lawrence, to the space there? Is space analogous? Is space gravity?
Well,
Is what we call space really gravity?
General relativity has told us there's an intimate connection between what we think of as space and time and matter and energy, that the two are intimately related, that matter and energy affect the properties of space, and the properties of space and time affect the evolution of matter and energy. That's that nonlinear interaction that makes general relativity much more complicated than Newtonian gravity. So there is no distinction between, you can't describe space unless you describe, in some sense, the energy that determines the properties of space. And so when I wave my hands, as I do a lot, I'm creating a gravitational wave because we're all distorting space around us, and you can show, as Einstein first showed and then didn't believe and then believed, that when you have a moving disturbance like this, it creates a ripple in space, just as, although it's not the perfect analogy, just as throwing a rock in a nice, calm surface of a pond causes a ripple that goes on. So a gravitational wave is a wave in space, so the space itself oscillates.
I mean,
You should have answered that one.
Well, I'm going to try something that I don't usually try, but since you guys are holding up the physics end. So we know that there are these very subtle abstract things called electric fields and magnetic fields, and we can't see them. We think, right? But your phone's going to ring in response. Some of you are tweeting, doing whatever, and they're using the fact that those fields are permeating space. If you shake them, they create waves in the electromagnetic fields, and that's what light is, right? Light is a wave in the electromagnetic field. The analogy here is there is a gravitational field. We cannot see it with our eyes, but we experience it all the time. And if you shake it, like I liken the black holes that were detected to like mallets on a drum, and they're shaking space-time just like mallets ring a drum. If you shake it, you create gravitational waves, which is really very deeply an analog to light, but it is not light. No telescope can collect gravitational waves or take a picture of the gravitational waves. So we really needed to build this basically recording device.
I'm going to add one thing to that, which I think is a good description, which is that although it seems, in principle, it seems actually difficult to wrap your head around, it's actually more difficult to wrap your head around a world in which these waves didn't exist, in the sense that if I move something now over here, why, in high school you learn what the electromagnetic field is, but how did it get from that source to where you are? Does it do that right away? That would be kind of magic. The idea is that a field is what carries that information. So these black holes collapsed, 1 billion years ago, but that information has to travel to us. And so there has to be some rippling of the stuff that's in between, and all that's in between is space.
In fact,
it makes sense that there should be.
So there's, like we used to think, there was an idea that there was an ether back 100 years ago. So we don't need the ether because we have space itself acting as the medium to carry these things.
Einstein said you can have ether, but it was the question that Lisa just talked about was a really fundamental one. It's the one Newton asked when he said hypothesis non fingo. He said, I don't know how the Earth knows the sun is there, but I'm not going to worry about it.
Yeah, he knew he didn't know what gravity was.
Yeah, and it was only then, in fact, in some sense, it was the example of electromagnetism.
Right.
And the fact that Faraday said, hey, maybe the reason one charge knows another charge is there is that there's a field around it, and that discharge fields the field. That changed everything. Eventually came back to allowing us, through Einstein, to understand gravity. So it was really that
And if it
sort of
makes you
reverse.
feel any better, Faraday was someone who wasn't actually trained in mathematics. It's
He didn't.
an amazing
He didn't.
story.
Only wrote one
He just-
equation. He said in his whole life.
He just figured it all out, and then Maxwell put it all into equations afterward. But
Yeah.
he just basically was really lucky because he worked.
So what can all this discussion about the discoveries of dark energy, dark matter, black holes, what can this inform us about how the universe began? Does it tell us anything about how the universe began?
Well, this isn't exactly your question, but I just want to say when people talk about the discovery of gravitational waves, I want to emphasize it's not just another astrophysical phenomenon that was discovered. It is absolutely fundamental to the way we think of the law of nature works, that the gravitational wave, as Lisa was explaining, is the thing that carries information of the force to us. And so it's deeply, deeply embedded in how fundamental law works.
In fact, gravitational wave astronomy will be the astronomy of the 21st century in many ways, but in particular, it may be taking on this theme that that we only learn about the world by observing it, that learning about, we can talk a lot about how the universe began, and all of this informs us about the physics that's relevant, but what's interesting is when we look out with light, again, to follow up on what Lisa was saying in some sense, we can only see back to the point at which the universe became transparent, when it was 300,000 years old. Before that, it was opaque. If we want to look back to earlier times, we have to look at something that interacts more weakly than light. What interacts more weakly than light? Gravity. Gravitational waves from essentially almost the Big Bang could make it here. And 2 years ago, we thought we detected them, and maybe we will in the next year or two. They could give us direct information about what the universe was like a millionth of a billionth of a billionth of a billionth of a second after the Big Bang. So they will provide us the empirical data that allow theorists like us to continue our speculations and maybe.
Back to your question of how things started. I mean, I hate to tell you, but we don't know how things started, and there's good reasons we don't know how they started. First of all, things interacted too strongly for us to work it out. Second, we can't see back that far, but we do have an amazingly accurate story, we believe, of how things went pretty soon after the Big Bang. We know that dark matter played a big role, but we know in the beginning radiation played a role. Then we know dark matter took over, and at that point structure could begin to form, and then galaxies began to form, and there's a detailed formulation of that. And we're working out more about that, and that's one of the reasons the measurements today are so exciting. But we do have a pretty good picture, but from relatively later on, like fractions of a second after the Big Bang.
But technically, the Big Bang might have made a bang. I mean, in the sense that these gravitational waves are pretty close to an experience of sound, it was a pretty, we can model what that sound in the gravitational waves would have been, and it's pure white noise. It's a very just chaotic.
Right, let me just say,
if
you have a question, we got about 5 minutes for some questions. If anybody has a question, stand up now while somebody will get a microphone to you.
While they're getting the microphone, I just want to say that, in fact, that's what makes it exciting about learning back. The Large Hadron Collider takes us back to the universe, to conditions of the universe when it was about a millionth of a second old. So that's how far back we can go with direct detectors on Earth in some sense. And going back further, these other observations will allow us to take it back further.
Is there any new physics? Does the physics we have, everything we know, the formulations, is that adequate for us to...
That's what makes it so exciting. That's why we're interested.
So we
in
have
it.
jobs.
Yeah. No, I mean, we don't know what dark matter is.
I'm
We
going
can.
to take a different point of view.
Okay.
We don't know that. And basically what we as physicists try to do is we try it. I mean, you know, we try to come up with new theories, but really what we try to do is we work as hard as we can to see whether we can explain phenomena through existing theories.
Yeah.
And only then do we think we really have something new.
Are there missing
really
particles out there that we don't know about that comprise dark
They're
energy?
missing, we don't know about them.
We don't even know if they are. We don't know what we don't know.
Dark matter is unknown. I mean,
That's
that's all
what
there is
makes
to
that
it.
symbiosis so interesting, because there are dark matter detectors being built underground to detect this stuff, because if it's some new type of elementary particle, they'll go right through your body and my body and deep into the earth and look for it. But the Large Hadron Collider is also looking for it. We don't know which experiment is going to find it first. And as far as dark energy is concerned, all bets are off. I mean, no one understands dark energy, and it's going to be a lot harder to understand dark energy than dark
But
matter.
that's
So in
makes
answer
up
to your
most of the
question,
universe, though.
Yes, there probably is lots of stuff we haven't seen because we've only
Yeah.
probed so much. But no, we don't know that until we actually have evidence for
But we do know that dark matter is something we don't know what it is. I mean,
Right, but we
that's
don't
a
know
fact.
for sure, as we said earlier, we don't know for sure that it's a new type of particle. If it is black holes, it's
But it could be.
Okay,
What
but if
Janna said
it,
was important because it wasn't facetious.
Being very
We
conservative.
spent a long time trying to see if dark matter was something we knew.
I work
could,
in dark
like-
matter models.
yeah, well, like neutrinos, you know, there are we know of dark matter particles. We know that there are things called, for example, neutrinos, which do not interact with light, which
Yeah.
interact weakly in the way Lawrence is describing. But we can also prove that the ones that we know can't be responsible
Exactly.
for the dark
We
matter.
spent a long time, 50
Yeah,
years, trying to
it's
disprove
black
that.
holes,
So-
which it could be.
When we run out of the possibilities, we eliminate, it's like, well, it's going to be worse than what Sherlock Holmes says. When you eliminate all the things that are obvious, whatever is left is actually there. But when we eliminate those things, we have nothing left
Well, no,
to go
we
to.
do. We know that, what's really exciting is we know that the only things that are left are particles that are different than the particles that make you and I up. And that means there's more stuff in the universe than the stuff that makes you and I up. So it's incredibly exciting that we've eliminated all the stuff we know.
So the hunt is actually more exciting than the find.
Oh,
Often the
people were
case.
often disappointed that the Higgs was discovered. I mean, weirdly, everyone was thrilled because the Higgs was this piece of the puzzle, but there was also a sort of like, is that it? There was a kind of like, yeah, we did it. And then there was is that it? Like,
Actually,
we
back
want
to
to
the
discover new
introductory,
stuff.
like, conversation. It's really funny because on the one hand, we really want to think people are special, but on the other hand, this all acknowledges that there's so much stuff out there that we don't know. So we're special to us, but we don't know. That
Do we need new tools? If I'm going to give you a blank check question, my last question, I give on Science Friday to the scientists. If you had a blank check, you wanted to design something that could find out these things, do you even know what tool you need?
Well, we build what we can do. I mean, the gravitational LIGO was a great example of a tool that didn't even exist when people were trying to figure out how to build it. And we use the existing technologies, and we push them to their limits. The LHC is the most complex.
energy collider will find
Yeah,
something.
yeah. I mean, we'll need, and it's we know what we need to do to be able to explore regimes where we haven't seen. We don't know what we're going to find, and when we find something, that'll tell us what to do next. So
All right. I guess we have nothing to talk about anymore.
nothing
Thank you.
is-
We've run out of
nothing is
time.
very exciting. I want you.
Nothing is something from nothing,
Yeah.
right? Thank you. Thank you, Lisa Randall, Janna Levin, Lawrence Krauss. Okay, since we have our panelists, I'll assume we have anywhere. Everybody's ready to begin because we're going to move from the esoteric a little bit more to the concrete here. Concrete discoveries about things in our galaxy and outside of our galaxy. There have been some really exciting discoveries having to do with planets, which we'll focus on. And let me just I'll use the same model I did in the first panel. Everybody introduce themselves. Tell us what you'd like us to know about you.
Okay, I'm Alan Stern.
Alan, you begin. Yeah.
Hi, everybody. I'm a planetary scientist by training. I've been involved in quite a number of space missions, suborbital and orbital space shuttle missions as an experimenter, planetary missions, 27 of them now. My favorite is New Horizons, which just explored Pluto. In the last decade, I've become pretty involved in commercial spaceflight. And before that, I had the same job that John had recently, which is head of all of NASA's space science program.
Hi, Hi, my name is Lisa Kaltenegger. I'm the director of the Carl Sagan Institute at Cornell, and I'm fascinated by the search that we're right now undertaking for the first time in humans' history. We can spot the signatures of life on planets that do not orbit our own sun, but other suns. And that is also the core idea behind the Carl Sagan Institute at Cornell, looking at this from a very different angle with biologists, chemists, humanists, engineers, and of course astronomers in the mix. That we live in a time that we can actually, in a couple of years, figure out if we're alone in the universe is what fascinates me, and that we are the generation that get to live it, I think is what, in a way, will define our century.
John?
I'm John Grunsfeld. I grew up loving science, all kinds of science, and also wanted to be an astronaut when I grew up. I am an astronaut. I had the opportunity to fly on 5 space shuttle flights, 3 of them to the Hubble Space Telescope. I'm the Hubble repairman. Prior to becoming an astronaut, I was an astrophysicist, and at the time, black holes and neutron stars were really hot.
So to speak.
So to speak. They're still hot, but after doing the Hubble missions, I became much more interested in a field that was just started being a real field with the discovery of the first exoplanets. And so for the last decade or so, I've been working in exoplanets and actually trying to prepare the next generation telescopes that might actually be the ones that could find out the answer to that question, are we alone? For the last 4.5 years, I was the head of science for NASA.
Wow. Okay, let's work a little backwards now and talk about the exoplanets first. I'm going to read a quote to Adam Frank, you may be familiar with. He said, "It is not an overstatement to say that the discovery of exoplanets is one of the most profound transformations in human knowledge." Lisa, what do you think of that? First, describe how many exoplanets we have found. Where are they? What are they?
We know for sure that there are more than 3,400 exoplanets. It's a huge number and it's getting bigger every day. But to translate that, when you go out at night and you see the night sky, that's gorgeous here in Aspen, just count to 5. 1 out of 5 of those stars has a planet that is small enough to be a rock like the Earth, and that's at the right distance where it's not too hot and not too cold, so you could have liquid water on the surface. We call that the habitable zone, but it doesn't mean that life can only live there, but it means that the gases that life breathes in and out can escape into the atmosphere, and we can pick it up with the new telescopes we are right now building that John was talking about. So I wholeheartedly actually agree with that statement, because I think it is a world shift that now it's not a discussion over a glass of wine anymore that you share with your friends saying, "Ooh, could there be life? Could there be other planets?" The other planets, check. We know they exist around other stars, and you can see those other suns up there.
Wow.
Life is the next quest that we're looking for.
John?
When we think about human history and the discovery of exoplanets in that context, you can go back to a pre-Copernican world where the Earth was the center of the universe and everything else was something somewhat nebulous, but centered around not only the Earth but around people. And we then went to a solar system that had some small number of planets, and eventually we discovered all the way out to Pluto. But even in our own solar system, and we've discovered all these tens of thousands of asteroids in the main belt. Jupiter has over 60 moons. Saturn, we've seen rings around planets. We've now visited every planet in the solar system, including our recent exploration of Pluto. And Pluto is just one of
Probably 1,000.
Probably 1,000 Pluto-sized or roughly small objects out in the Kuiper Belt.
Yeah.
And it's not just now that when you look at the night sky, virtually every star in the sky has a solar system around it. They're probably something like our solar systems. They probably have some giant planets with hundreds of moons.
So there are billions of them out there.
Probably hundreds of billions.
Hundreds of billions.
I believe that, and we'll hear a little more, but I believe that the the current paradigm is that most every star has a number of planets. So there are 100 billion plus stars in the Milky Way alone. There are hundreds of billions of planets in our galaxy.
Let's talk about Pluto and your specialty now. I mean, I don't know if it was you or reading or another scientist who was they're so excited about what you're seeing on Pluto. Someone said Pluto is alive. Was that your quote or someone else on your team?
I said that, and I meant geologically.
Talk about what is so exciting. You've made so many discoveries, or the spacecraft has sent back so many wonderful pictures.
Yeah, one of the things that I said right after the flyby when we got the first images that showed us just how complex a world this was, 3 billion miles from home and on the frozen frontier of the solar system, is that the solar system saved the best for last. Really, the physical beauty of this place with a blue atmosphere, with hazes in the atmosphere, with mountains as tall as the Rockies here in Colorado, and evidence of liquids that float on its surface in the past, and many other things, including active surface geology at the present era, 4 billion years after it was formed, is something out of a science fiction novel. It's something more than any of us expected to find in doing this exploration, and yet it's what nature has wrought and brought. And fortunately, our species, and in particular our country through NASA, has undertaken these explorations to understand our home solar system, and someday I hope we're exploring the other solar systems of the galaxy.
Well, let me get into that. If you're looking at exoplanets, or if you're even looking in our solar system, how do you find signs of life, past or present? Let's talk about the exoplanets first.
So what we're trying to do is, well, we look at the planet that we know has life, the Earth. And then we look at the ones that don't, like Venus and Mars, at least currently. And then we say, okay, now to moons, for example, like frozen moons like Europa, that has a subsurface ocean where there could be life, you could fly in our own solar system, we hope we're going to do this pretty soon, drill a hole and figure out if something's swimming around. But if you now move these planets and you move them to another star, they are very far away. And if you want to think about this, if you actually take our whole solar system and shrink it in your mental eye to the size of a cookie, the next star, the closest one, is 2 football fields away. So the only thing we have is actually light that we can catch in our telescopes and analyze. And it basically works this way. When the light of the star gets filtered through a planet's atmosphere, it encounters molecules and atoms while it does that. Light is energy. When you go outside, it gets hot. And so if the right kind of energy hits a molecule, it will start to vibrate, to swing, or the electrons will get chucked up in another higher energy state. And when that happens, when we look at that light getting filtered through the planetary atmosphere, there is some of the light missing, the one that was used to excite a molecule, for example. It's very specific for each molecule because, of course, O2 has 2 O's, so it swings very differently than water, H2O, that has 3 pits. And so just by the light that we can collect, that it's filtered through an atmosphere of a planet cosmic football fields away, we can tell you what's in the air of that planet and if something is breathing there.
Wow.
And let me just say, it's super interesting that we are on the verge of having this technology to be able to not just discover planets around other stars and discover their orbits, but to start to probe their properties and even look for telltales of life. But one of the most interesting discoveries I think we've made in the 2 generations of planetary exploration in our solar system is the discovery that oceans are common in our solar system.
Ocean, water, ocean?
Water oceans. At the beginning of the space age, when astronomers and planetary scientists looked only through telescopes, they saw solid surfaces everywhere. But now through spacecraft exploration, we have discovered that ocean worlds with oceans on the inside,
Give us some
are
examples.
common, like Europa, Jupiter's large moon, like Enceladus, Saturn's small moon that has an ocean on the inside, Pluto that almost certainly has an ocean on the inside, and half a dozen more. It's the Earth that's the oddball that wears its ocean on the outside. And we're going to have a really tough time finding life in those abodes around other stars, and yet that could be the most prevalent
Wow, that's
of
that's the tweet of the day. Earth is the oddball. It's got its oceans on the outside.
Well, except Mars used to, or at least large
Yeah.
seas.
Yeah.
That's another good point.
But I think that the key point that Alan is pointing out here is this is why we need to use everything we know about the planet, our own solar system. You know, we don't have any more info, and then we throw all the physics that we know at the problem to explore what else it is we could see. And as Alan was saying, there could be a vast majority of bodies out there, icy moons around other planets, that could harbor life subsurface. For now, we don't know how to spot it, because we need the gases to be able to escape into the atmosphere and change that stellar light for us to pick up signatures for life. But there's billions, if you want to go that way. You know, this is a very just going out. There's billions and billions of possibility out there that I can't tell you whether or not there'll be life. I don't know if there's one on Europa.
I love it when a scientist from Cornell says billions and billions.
Billions and billions.
So let me cast this in a slightly different way. Let's do a thought experiment. Let's imagine that we are on a planet around a nearby star that's maybe 10 or 20 light years away, the distance light would travel in 20 years. That's actually quite far, but by galactic standards, close. So
Is there such an exoplanet?
So well, there almost certainly is.
Yeah.
No, but the ones that we found in the
There's ones we
habitable
found.
zone.
But let's say there's one that's
Okay.
just like Earth.
Okay.
It has an advanced civilization, so we're inventing this. And they have built a telescope that's just a little bit bigger than what we're building today. And they look back at us. What will they see using this technique of looking through our atmosphere as it goes around the sun to look at this missing light and the colors that they see? And what they would see is they would see that we live on an ocean world. They would see water vapor in our atmosphere, and they would see actual color changes in our planet as continents and oceans come into view. So they would know we have continents and oceans. If they watch us for a few years, they would know that we have polar caps that grow and shrink with the seasons. They would know that we have a lot of oxygen, and they would find that very interesting. They would know we have carbon dioxide. They would also see the evidence of industry. They would see the chemical pollutants in our atmosphere that they know are not geologically produced.
When they hear our TV shows and radio shows?
We broadcasted for such a brief period of time, they probably would blinked and missed it.
Carl Sagan used to talk about I Love Lucy is reaching Alpha Centauri about now or something like
The
that.
key thing about thinking about this, life on the Earth was around for more than 3 billion years, right? So radio or our signals are a very fraction of that. But about 2.5 billion years ago, life started to make oxygen, this really telltale, intriguing combination of oxygen with reducing gas. That's what tells us that something produces this oxygen in huge amounts, or it would actually react with methane to CO2 and water. And therefore, that's our key to say, there's life as we know it. We'll miss a lot of life.
But there's a difference between life and then intelligent life.
Well, certainly these people looking at us seeing the pollutants would rule out intelligent life.
Yes. And actually, going along that line, one of the things when we were looking into what could you look for an industrial civilization, so you want somebody who's more advanced and so on, what came up were freons that come out of your fridge and actually destroy the ozone hole, right? But you'd have to have more than we have for actually to pick that up. And then we were actually starting to discuss whether or not that's a signature for life or the reverse. They haven't figured out that the ozone hole gets killed. And then the question was like, at what level of freons are you intelligent, and what are you have you actually?
If there is something 20 light years or 40 light years away, that raises the possibility in my mind that if there is intelligent life, we could actually carry on a conversation within one person's lifetime.
And think of how much money it would save, because if, referring back to the former panel, if we were to find an advanced intelligent civilization around another star, we could simply ask them, what are black holes? What is the source of gravity? We could get all the answers just by asking.
But some people
save all that money.
They might think that we're just like ants. We're too stupid to talk to if there's such an advanced civilization. You know, why communicate with these people on Earth? Because they're still doing this sort of thing.
You're right. We could carry on a very short conversation, but a conversation nonetheless.
Mm-hmm. What's going to happen to New Horizons now in Pluto? It's going to go past Pluto? Well,
there are two answers to that question. New Horizons is operating perfectly, And we hope to carry on an exploration of the entire third zone of our solar system called the Kuiper Belt over the next number of years. And the spacecraft's capable of that, and we've proposed it to NASA. So NASA will make its decision. And if it does, then our next flyby is on January 1st, really easy date to remember, 2019. But then there's the longer scale question, what will become of the Voyagers and New Horizons that are leaving the solar system and emerging out into the galaxy? And we don't know of anything that should cause them to be destroyed or even to really age in that cold vacuum environment. They could outlive the Earth, very much. Yeah. Outlive our own planet, our own home planet.
It could outlive our planet.
Which is an amazing thought. When the sun goes red giant and the Earth becomes a cinder, those spacecraft that we sent out, like New Horizons and Voyager, will be completely unscathed because they're so far away. Pretty amazing.
I think also one thing to add to that is our search is not just a search for life, even so that's extremely exciting. But with every planet we will find, and we'll need a bigger telescope like the James Webb telescope that's coming up, 6.5 meter, twice as big as this, that we're launching in 2018 into space. With every planet we find that is like the Earth, we'll figure out a little bit more how the Earth really works. If we have older Earth that we can look at, if we have younger Earth, we figure out how our own pale blue dot works and how to safeguard it better and to extend the lifetime a little bit that we have to actually live here and then find a way to explore space and travel and seed space if you want. Like in the far future, with 1 billion years, without climate change, we have 1 billion years to figure this out. But we'll have to figure it out because the stars tell us that a sun, like our own, actually becomes bigger and bigger. And so at one point, it will be as big that you basically can nearly touch it from the Earth. That's how big our sun is going to be.
It's not anytime soon.
No, I said we have.
Right. I just want to make sure people don't get excited about it.
That's true.
And actually, you really don't need to worry too much because we're going to collide with the Andromeda Galaxy before that becomes a really serious issue. So.
It's a question which one's going to get us first, right?
What you mentioned that the Hubble. I think the Hubble Space Telescope and the rovers on Mars, I think, have done more for for the public excitement about space exploration than anything since people walked on the moon, I think. And now we're talking about, you mentioned the Webb telescope, which is the next telescope. What will that see? What is it made to see? Is it made to see exoplanets more than anything else? What can it see that the Hubble can't see or won't?
Well, let me start off. The James Webb Space Telescope was originally conceived to go where no Hubble has gone before, which is Hubble sees in visible light the same colors that we see. And as the universe expands, very distant objects, distant galaxies, the very first galaxies, the light gets stretched out and more red. So Hubble is really seen to the limit in the early universe of what it can see. And the question is, well, what's beyond that? And so we had to go to an infrared telescope, to a more red light, to be able to probe even further back. So James Webb was envisioned to see what Hubble can't see, the earliest stars and galaxies, to try and maybe see the first galaxies that ever appeared in the universe, the first stars, to see if maybe black holes came first before normal stars, and then watch the evolution and the construction of these stars and galaxies. Also, inside of our own galaxy, there are places where light can't emerge. Inside of large molecular clouds, gas and dust, where new stars are formed. But infrared light can sneak out, and so we'll be able to peer into these stellar nurseries with James Webb Space Telescope. But the remarkable thing is, when James Webb was designed, we hadn't discovered any exoplanets yet, the critical thinking about it. But it turns out if you wanted to build a telescope that was perfect for looking at the atmospheres of planets around nearby stars, you would design something just like the James Webb Space Telescope. So we got really lucky.
You might want to design it a little bit bigger, but I agree with you. So the first step at this
No one's ever happy with what they have.
You give the other people a check, right? So we want one too.
Let me tell you that story just briefly, because the astronomy community, not being particularly big risk takers, they said, well, we think the biggest telescope we can get away with after Hubble is instead of 2.4 meters, we'll double it. We'll make it 4 meters. And they described that to Dan Golden, who was then the administrator. And he said, this telescope could really, make tremendous discoveries, why stop at 4 meters? Why don't you ask for an 8-meter telescope? And so that's what went forward, and eventually from a number of technological reasons, it shrunk down to 6.5 meters. And that's sort of the cautionary tale.
I got it.
Sort of like, let's build an accelerator, but let's not build the Large Hadron Accelerator. Let's build something that's only a little bit more energy than, say, Fermilab. We wouldn't have seen the Higgs.
Like a super collider or something like that.
Yeah.
Alan, let's talk about, you mentioned that we are the outlier in the ocean world in our solar system. Are we going to visit those oceans? You mentioned on those moons of Jupiter and places like that.
Yeah, in fact, we have missions on the books right now that are being designed to explore Europa's oceans from overhead, from spacecraft that will make close flybys, look for geysers coming out of the oceans, probe the interior of Europa in ways that we've not been able to with past missions. Those are already on the books for launch in the early 20s, which is not very far off. But there's also an initiative now in NASA and in the scientific community to go beyond that, to study ocean worlds more broadly in our solar system and to fly missions potentially to Titan and Enceladus and other places where there may be habitats deep below the surface of these small worlds. It's pretty exciting.
You must be excited having studied all of these things for so many years.
Well, I mean, people have wanted to go back to Europa since Galileo did its 11 flybys. Everything we know about Galileo is essentially from just these little short visits. And just last year, we were able to officially start a mission to Europa, hopefully launching in 2022-23 timeframe. And we're now not only studying the orbiter, but a lander.
A lander on Europa.
In addition,
Drill down into the water?
Well, actually, just to land and reach out and sample the water.
How did Arthur C. Clarke get this all right?
Well, actually,
he talked about, when 2001 Space Odyssey, it was Europa that they went to.
I have to tell you one story about a scientist, Fred Ordway III. He was the scientific advisor to Stanley Kubrick and Arthur C. Clarke, because Arthur C. Clarke knew that the radiation environment at Europa would be too hazardous by huge amounts to send a spacecraft, and he had the spacecraft going to something like Enceladus around Saturn. But at that time, 1965, 66, the artist couldn't animate the rings of Saturn in the film, and so Kubrick convinced them to make it Jupiter and Europa.
Wow. Maybe he's a black.
This is how we get things right.
Well, I mean, you have to admit that science fiction writers have been pretty good at inspiring.
Well, certainly Arthur C. Clarke has been.
But I think a lot of the science fiction writers that I know actually are physicists or astrophysicists, astronomers, or people who are really enthusiastic and follow the literature and then just spin it further. And I think this is also where artistry, in a way, and literature intersects with science, because a lot of us, at least me, I got inspired by science fiction, by Carl Sagan's Cosmos, right? This is things that bring out this fascination of exploration for me.
If anybody's
Those
any
worlds
questions they
exist.
want to ask, we'll start to take some questions. Just stand up or raise your hand, and we'll get a microphone to you. I didn't need to,
I would say one of the most prescient things I've ever heard science fiction writers say is that the universe is not only stranger than we imagine, it's stranger than we can imagine. And certainly with every chapter of exploration, through telescopes and through spacecraft that actually go to these places, we've discovered that that's proven itself to be true. It's always stranger than we imagine. We always underestimate the richness of
certainly with Pluto, that was the case.
Exactly. That's a case in point.
It is so much more fun, and this is also what the panel before us said, to discover unimagined things, because this is how we learn. If all solar systems were like ours, it would be pretty boring. But we're finding such a diversity that teaches us about how planets form, which ones could have life,
Right.
and all this spins together.
So much for dreaming. Let's talk nuts and bolts and dollars and cents or euros and pounds or whatever you want to talk about. Do we have the money, the political will, whatever, to do these explorations, to go to the moons of Jupiter or maybe Enceladus or whatever, and conduct these explorations we're all talking about?
Clearly we do, because we already do it. John managed a program that probably had the better part of 100 space missions in astronomy and planetary science, earth science, under his wing. When I was running the same program, same scope. But I think that we're going to see an even bigger effort in the future, because as private industry comes in and looks at missions to asteroids, to the moon, to Mars, and maybe to farther away places, we're going to see the other side of the economy, not just the civil side of the economy, but the commercial side of the economy come in and start to invest in space missions to many locales.
Do you think Elon Musk can get to Mars by 2025?
Absolutely. I don't know about 2025, but I'm sure that he'll do it if he wants to. He said that he would develop electric cars, and he did it, and a lot of people laughed him off. He said that he'd develop the lowest cost launchers to Earth orbit, and he failed a few times at first, but he kept going. People were very skeptical, but he did it. He is driven by this, and I would not bet against him.
Well, I don't want to be too controversial, but we did have electric cars in 1890s. It's a practical, producible car, and the jury is still out on that. And even though he is selling the Falcon 9 launchers for the lowest price, the actual cost is still as high or higher than Atlas and the other rockets. This is, the really interesting time is, can he scale it up in either case of cars, rockets, other areas to generate a commercially viable business? And we all hope he does. What I find really exciting about it is that his motivation for doing this is not because he wants to make a profitable rocket company, although I'm sure he does, but it's because he wants to use this to leverage then his real dream, which is to go to Mars.
And what's exciting is something that David Aguilar said at the beginning, is that we don't have to pin our hopes on Elon, although I'm a big believer in what he has been able to accomplish and what his goals are. We have Bezos, and we have Branson, and we have many others now that are coming online that want to invest the same way, either in mineral resources or exploration or in human colonization. It's going to be an exciting century.
So you think then it's going to be private enterprise that gets there before any government or multi-government funded?
I don't know if private enterprise will beat the civil side or not, but I think that the private economy is going out into the solar system, and many businesses will fail and many will succeed, just like aviation in the 20s and 30s. But I think they'll transform the world.
Let me flip back for just a moment, though, that it's not a question of who's going to beat whom. I mean, we're on Mars today. I mean, we're driving, as we speak, on Mars with the Curiosity rover. We have another rover on its way. We've just passed Pluto. We're heading out to another object. We've got Cassini finishing up its mission at Saturn, which is with an entirely new one. I mean, we're throughout the solar system, and we're going to continue to do that. I think the really interesting message is we have lots of debates about human space flight and where are we going to go and when are we going to go. But at the same time, the science program, as Ellen described, has been enormously well supported by the American people, by the Congress, both houses of Congress, both political parties. This has been a very strong, all of the guests that we've had on Science Friday.
Isn't there a bill now in Congress to tell you where to go? There's a fine print in a bill that says you will go to and sell it?
Well, this is not uncommon. In fact, yes, there's a bill in Congress that has legislation that NASA will explore Europa, Jupiter's ocean-bearing moon that we just talked about. But back in the 1960s, there were bills that were written following John F. Kennedy's announcement that said you will send humans to the moon. So this is not new.
I think also I would phrase your question a little bit different. Are we going or not? If we were to find a planet that could be a habitat very close by, I give you 20 light years, 10.
Right.
Then it becomes a question for every one of us. Is that interesting and important enough for us to actually find out more? And I think at the heart, and David was talking about it a little bit, we are explorers. We're trying to find new things. It has always been good for the whole human species when we made this next leap.
Wow.
And it might be commercial right now, it might be private, but it's the thing that's next.
All right, let me get a question from the audience here.
Well, thank you very much. One of the many interesting things I hadn't heard before is that the Milky Way is going to collide with the Andromeda Galaxy before the sun kills us all or destroys the Earth, becoming a red, whatever it is.
Giant.
Red giant.
Giant. Could you explain the timescales again? I think you mentioned them quickly for those two things. And if the galaxies actually collide, then what happens? Does that destroy us, or does it just make it a more interesting galaxy?
Actually, it was just an interesting factoid. But in fact, the Hubble Space Telescope has precisely measured the motion of the stars in the Andromeda Galaxy. And we've been able to know, roughly that we're in sort of an orbit around each other. But now we know that actually we are on a direct collision course. And it's going to be fascinating because we have the Milky Way now, which is the plane of our disk of our galaxy we're looking in. And we're going to start to see Andromeda, which you can see perhaps from Aspen naked eye now. But it's going to get bigger and bigger until it fills the night sky. And the combination of both galaxies is going to be such that you'll be able to read a book at night if you were here. But the scale is a few billion years.
Let me just.
I think, can I just add to that? So I agree with the Andromeda, but I have good and bad news. The kind of bad news is that in about 1 billion years, it's not when the sun is going to be so close that we can touch it, but it's going to be strong enough because a star brightens that we're going to enter something that we call a runaway greenhouse, where we evaporate all of our ocean. But we have 1 billion years. So the good thing is we might start to be able to read something in Andromeda's light, but we definitely have to get off this planet before the galaxies collide.
If you think we have water problems now, just
in a few minutes we have left, let me.
The other is when two galaxies collide, they mostly just go through each other.
I got you.
It's usually not bad.
Well, Lisa, you seem pretty sure that we're going to find signs of life in one of these. How do we prepare the Earth people for that? For finding life? There is life other places in the universe.
This is, I think, where I differ from that Contact movie, where they think it's going to be worldwide panic, because we found the first planet around another star 22 years ago. Any teenager you talk to has never lived in a world where there weren't other planets, where they weren't sure there were other planets. So from that to that there should be life out there, it's a small step, and that's a huge generation.
Well, let me push back a bit.
Okay.
We live in a country where 56% of us don't believe in evolution. How are we going to convince them that there's life on another planet?
Well, I think one of the things that we're doing not so great a job of sometimes communicate the fascination of science, especially to school kids that start to get bored with physics and math. And I think this is one thing where we need to do better, because they will tell their parents how fascinating it is, so we get those people, and they will be the inventor of the futures.
Okay. Somebody had a question here? Here? Over here. Let's go to this gentleman over here. Somebody behind you. Look behind you. There you go.
Yes, my name's Robert. I come from Dallas, Texas. I want to follow your point that there are millions of opportunities out here, and I think the challenging question is that you started to address, if we got a message tomorrow from one of those planets that they were somehow able to communicate at the same wavelengths that we could understand, or in a way that we understand, because they may have been trying for many, many years and we don't know how to receive it. But then they figured out how we receive it. What is going to be the reaction of people on our planet to that message?
I think the good thing is, again, when you go to the cookie and the cosmic football fields, most things are really far away, so panic is not what you have to go with, because it takes a lot of time. And honestly, in a way, we are not very interesting. You don't want to get our water, you catch an astronaut for that. Asteroid for that.
That too.
And we don't have any resource that anybody would have to come after us for. So this whole horror movies with sci-fi, that's something that we make up because of really good movie going, right? You want to go with
I think the question is a very perceptive one on another level, which is, I think that if your thought experiment were to come true tomorrow on Tuesday, what you would see first is a wide spectrum of reactions. Some people would be enthralled and inspired, and some people would be horrified and terrified by it, and everything in between. And that it would then evolve over time based on what they're telling us, and we're able to learn about them. But I still think it will involve a wide spectrum of opinions, just like we have in the public about many other topics. And I don't think we'll get one reaction, a uniform reaction from the public.
56% of Americans will call it a government hoax.
So we'll be fine, they won't panic.
Any other questions from right here, this gentleman right here?
Hi, I'm this idea of all these exoplanets, which were theoretical but now proven, and the idea that there could be, did I understand, 50 billion Earth-like planets in our galaxy alone?
Or more.
Or more. It reminds me of the famous Drake equation, And that's one of the factors, I think, is how many of a certain kind of planet might there be. And now that that's no longer pure conjecture, how does that affect our calculations about the probability of life in our galaxy and your own feelings about that?
So the really interesting thing about this is that we usually joke and say the astronomers have done their job, so now the biologists have to figure out how often life evolves and so on. But this is what, for me, makes this question so fascinating. Because if we were to find no life anywhere, and we, within the period of time, the next 10 years, we'll figure out if life is rare, if we don't find it on any of the planets around us, or if it's very common. So both answers to me are fundamentally fascinating. And the Drake equation captures the different parts, but the search that we're doing will put a number on this. And then from that, we can actually tease back how often does life evolve? Always, never, very, well, once. Or how long does a civilization live? I think all our conjunctions, what we think, how long a civilization could live, are just that. Conjunctions, ideas we have, but we have no strong footing except to say, we live this long. That's the minimum.
There is something called the Fermi paradox.
So where is everyone?
Which is, where is it? There's so many civilizations out
And
there.
it may be as simple as they're all living on subterranean ocean worlds.
Yes.
We just can't detect them. So, we can only sense with the techniques that we have. Those are biased to certain types of ecosystems. And there's a selection effect in what we can do and what we can't do. So a negative answer doesn't necessarily mean that there's no life across the galaxy. It could be quite common, but just hiding beyond the reach of our techniques.
And if you wanted this last thing,
Last word.
around. If I give you 2 planets, and it's incredibly hard to communicate or to actually go there, and one is more advanced than we are, and one is less advanced than we are, which planet would you want me to go after? And now turn it around. We have only stepped onto the moon. We haven't even made it with man to Mars. We are not interstellar. So why would anybody, if there's a lot of planets out there that are interesting, contact us to try to figure out what we're doing?
I like our ocean. Thank you. We ran out of time. Fascinating conversation. Thank you all. Alan Stern, Lisa Kaltenegger, John Grunsfeld. Just the beginning. We'll see you on Friday, Science Friday.